today's STERIS Tech Talk on the fundamentals of VHP. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is Ashley Marute, and I'm the Associate Product Manager for STERIS Applied Sterilization Technologies. I'll be the host for today's event. Our presenter today is Conor Pardy, a VHP Sterilization Engineer for STERIS Tullamore, Ireland. With a background in microbiology, Conor joined STERIS AST 2 years ago and has spent that time developing vaporized hydrogen peroxide as a fully integrated technology within the STERIS AST portfolio, through both carrying out research and development studies, as well as developing a full quality management system for the technology. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS Applied Sterilization Technologies YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Conor to begin the presentation.
Thanks, Ashley. Hi, everybody, and welcome to this STERIS Tech Talk on the fundamentals of vaporized hydrogen peroxide. As Ashley just said, my name is Conor Pardy. I'm the VHP Sterilization Engineer for STERIS Tullamore, and I'll be going through this presentation with you today. So the agenda for today's webinar is to understand the background of VHP, then look at an introduction to VHP sterilization as a modality in itself, and then finally to get an overview of how VHP is currently being used. As VHP is the newest technology that's been added to STERIS AST's portfolio, I'll just start off with why another gaseous sterilization technology was needed. So ideally, if a device could be irradiated, it would be, but for material compatibility reasons, gas modalities are still required, as can be seen by how ethylene oxide takes up about 50% of the sterilization market at the moment. And this is because products can have things like electronics that be fried by radiation, or maybe polymers that might be made brittle. So gas technologies are still required. As well as this, STERIS always tries to be both technology neutral and technology diverse, meaning that we have the widest range of technologies to choose from that we can, so that rather than trying to make your product work for a set technology, we can pick the technology that will work best and fit any sensitivities your product might have. So with this, a lot of latest generation products also tend to pose a lot of new challenges. So with being sensitive to things like temperature, humidity, radiation, and so on. And therefore, the more technologies that we have to choose from, the more likely it is that we'll have something that will work for your product. So with all this in mind, vaporized hydrogen peroxide just provides another option for medical device processing that we can look at if your product can't be processed with gas or with ethylene oxide or radiation. So then where does VHP fit in STERIS AST's portfolio? As I said, VHP is the newest sterilization modality in the AST portfolio. It's been brought in as an additional gas or vapor sterilization method. So up until now, we had 3 sterilization technologies that for use with radiation in our electron beam, gamma radiation, and X-ray technologies. But before this, we only had the one gas technology in ethylene oxide. So by bringing VHP in, we just provide another alternative option to choose from. So if your product can't be processed with radiation, but might have, say, an electrical component that makes it unsuitable for use with ethylene oxide, VHP is now just another choice that we can look at. VHP then is mostly applicable to smaller volume niche products, things like novel device designs, pre-filled syringes, and drug delivery devices. It's not, however, suitable for everything. So the main challenges we see with VHP are around cellulose materials and long lumen devices. The problem with cellulose is that cellulose is quite absorptive. So if you have, say, paper, cardboard, or wood, the cellulose in that will absorb up your hydrogen peroxide vapor. And therefore, if, for example, you have a product inside a cardboard box, the cardboard of the box will absorb up a lot of your hydrogen peroxide vapor, meaning that you're not going to get the full dose into the product inside. And on top of this then, once that cardboard box has soaked up the hydrogen peroxide, it's going to be a lot more difficult to get it out of there again at the end of the cycle. The issue then with long lumen devices is that VHP just doesn't penetrate quite as well as ethylene oxide. So it's pretty good at most lumens, but for example, if you have something that's 2 or 3 foot long and only a couple of millimeters wide, VHP will struggle to get down the length of that lumen. And there are ways of working around that through, for example, changing the temperature or the amount of VHP injected into the cycle, but there's only so much we can do around that. So with this in mind, and with how VHP is the newest modality in our portfolio, it does still need some further development to fully position it in the medical device terminal sterilization market, as well as come up with strategies to overcome these challenges that we're seeing at the moment. Finally, then, just to note that the addition of VHP to STERIS AST's portfolio of technologies has also led to a lot of cooperation between our AST and Life Sciences divisions, as STERIS Life Sciences are actually the ones who manufacture and sell the VHP sterilization chambers. So as a result of this, there's been a lot of collaboration between our divisions as we share any developments that we make between us, and as well as help out with different customer projects. So for example, if a customer is purchasing a VHP chamber from STERIS Life Sciences, while that chamber is being manufactured, they can come to ourselves in AST and we can help them to develop process challenge devices or identify process parameters so that as soon as they get their chamber, they're ready to go. So then basically what is VHP? Well, VHP stands for Vaporized Hydrogen Peroxide. However, VHP itself is actually a trademarked STERIS term. So outside of STERIS, you'll usually see this referred to as VH2O2, as that's what ISO refers to the technology as. VHP is a vapor or gas sterilization process, as you can probably tell by the name Vaporized Hydrogen Peroxide, and it works as an oxidizing agent. The sterilization process then operates under deep vacuum and low temperatures, and while it is pretty brand new to the terminal sterilization industry, it does actually have a long history of use within the healthcare industry and hospitals, and I'll go into that a bit more in a few moments' time. The basic principles then of the actual sterilization process itself are that VHP is a low temperature dry vapor process. So our typical temperature range is between 28 and 50 degrees Celsius. And there is some room to maneuver outside of that, but there is always going to be some sort of a drawback if you go above or below that range. So we tend to stick between 28 and 50 degrees. And it's a dry vapor process because we have a set humidity limit within our cycles to make sure that there's no condensation or anything forms during the cycle and it remains dry throughout. VHP is effective against the full spectrum of microbiological contaminants. So it works with bacteria, viruses, fungi, the whole lot. And hydrogen peroxide itself breaks down naturally into water vapor and oxygen. And this is sped up in our post-conditioning process by use of a catalytic converter. But this just means that we have no issues then with fugitive emissions or carcinogenicity or anything like that, as water and oxygen are themselves essentially harmless. And when we process products with hydrogen peroxide, we don't see any problems with material discoloration or other negative cosmetic effects, such as brittleness or anything. And as this diagram here then basically shows, we start off the process with a 35% liquid hydrogen peroxide solution, and this is then vaporized, and that vapor is pumped into the sterilization chamber along with the product. At the end of the cycle then, the vapor is removed again from the chamber and passed over a catalytic converter, which breaks it down into water vapor and oxygen, so that we have no issues again with fugitive emissions or anything like that. And at the end of the cycle, we make sure that any residues inside the chamber are kept within specified acceptable limits. However, there aren't actually any regulations around these acceptable limits, so it does depend on your own local health and safety guidelines. So for example, in Ireland, our acceptable limits are 1 part per million over an 8-hour time-weighted average, or 2 parts per million for a short-term exposure limit. As I said previously, while VHP is pretty new in the terminal sterilization market, it does have a long history of use in the healthcare sector. VHP has been used in the healthcare setting within hospitals for over 30 years now, and the STERIS V-Pro is actually a significant player within hospital sterilization using VHP. These are mostly used for sterilization of reusable medical devices, so things like endoscopes that can be processed again and again for reuse. And because there is such a history of VHP being used within hospitals, there has been extensive material compatibility studies carried out. And I'll talk a little bit more about that in the next slide. One difference between the use of VHP within hospitals and with what we'd see in the industrial side is in the scale of it. So, for example, the largest size of a STERIS V-Pro that you can get at the moment is 136 litres, whereas what we'd be seeing is in the thousands of litres. Also then, just note that in the current COVID-19 environment that we're in, the FDA has granted STERIS emergency use authorization for the decontamination of N95 and equivalent respirators using VHP with the V-Pro systems for up to 10 times. So VHP has actually proven itself very useful for the current situation that we find ourselves in. Around material compatibility then, to break it down to quite simply, VHP is very compatible with most plastic materials and glass. The only thing being that softer plastic materials tend to absorb more hydrogen peroxide, while harder materials absorb significantly less. And this just means then that if your product has a lot of soft plastic in it, it might just need some extra time to post-condition at the end of the cycle to remove all the hydrogen peroxide from that again. VHP is also compatible with most metals, and it does not penetrate through materials, so it's strictly a surface sterilant. So for example, if you have a pre-filled syringe with a sensitive drug inside, VHP would only sterilize the outside surface of that syringe and won't penetrate through to the product inside. As VHP is a strict surface sterilant, that does mean that our product packaging needs to have a breathable layer, such as Tyvek, which will allow the VHP to pass through and reach the surfaces of the product and then be removed again at the end of the cycle while maintaining that sterile barrier. And the only real material incompatibility we have with VHP is again around cellulose, so with paper, cardboard and wood. The problem with these being that they absorb up the hydrogen peroxide, which then weakens the sterilization effect around the surfaces. So as I said, if your product is in a cardboard box, the cardboard of the box will absorb up that hydrogen peroxide and you're not going to get your full dose to the product inside. So if you're looking for more information around material compatibility, AME-TIR 17 is actually a technical information report that looks at the compatibility of materials subject to sterilization with a range of different modalities, and this does have a section dedicated to hydrogen peroxide. The equipment we use then for our VHP sterilization, as I said, is manufactured by STERIS Life Sciences. So in this case, STERIS Finaqua in the Helsinki area of Finland. And they provide a range of vessel sizes going from the equivalent of a half pallet chamber to a 4 pallet vessel. And the chamber that we have in our Tullamore site here in Ireland is a 1 pallet chamber. So the thing with these is that they're much smaller than you might see with an ethylene oxide cycle, actually the ethylene oxide chamber. So we're never going to have a 16 or 32 pallet VHP chamber, but there are other ways of counteracting that. So for example, our typical cycle times that we see with VHP are 3 to 6 hours, although these do depend on the product and the application being used. So if your product is more challenging to process, that means we'll need more time in the sterilant exposure phase, which then needs more post-conditioning at the end. But typically we'd see that cycles tend to be between these 3 to 6 hours, so these are a lot quicker than you would get with a larger EO chamber. Our processes then take place under a deep vacuum of 1 to 10 millibars, typically 4 millibars, what we usually see. And this then is something to bear in mind when you're looking at VHP compatibility for your products. It's just making sure that the product and its packaging are able to withstand that low pressure. Our process temperature range then is between 28 and 50 degrees, with our average cycle taking place at around 35 degrees Celsius. And we then have a set relative humidity limit within our chamber to make sure that the process remains dry throughout and there's no condensation. And this limit is typically then 80 to 95%. And the thing with the humidity is that while we do want to make sure that there's no condensation forming, the higher you allow the humidity to get, the higher the concentration of VHP you get within the chamber. So we have to kind of toe the line in between those two. Sterilant exposure then with VHP is subject to pulses, which I'll go into a bit more in the next slide, which is a bit different from how you might see with an ethylene oxide cycle, where in EO you just put in one pulse of EO and then keep it at that level for a set dwell time. In VHP, we do multiple pulses of this. Finally, then at the end of our cycle, we make sure that our residues are kept within specified acceptable limits, both for batch and operational safety. So for ourselves here in Ireland, that means that any residues inside the chamber at the end are within the 1 part per million over an 8-hour time weighted average, or 2 parts per million for a short-term exposure limit. This diagram here then shows a typical VHP cycle structure. So similar to an ethylene oxide cycle, a VHP cycle is split up into 3 phases. So we have a conditioning phase, a VHP exposure phase, and then a post-conditioning phase. And all 3 of these phases take place in a single chamber, one after the other. So there's no delay or movement in between them. So there's no conditioning in one area, VHP exposure in the next, degas somewhere else. And we'll start then with the conditioning phase, which is basically just where we bring the product to the set temperature we're going to process at. So if we're going to go at 35 degrees Celsius, we make sure that the load is at 35 degrees before we go into the exposure phase. While this is being done, then we run a quick leak rate test where we just pull a partial vacuum, hold that there for a few minutes to make sure that there are no leaks in the chamber before hydrogen peroxide gets introduced. And then we'll go back to atmospheric pressure before starting into the exposure phase. The exposure phase then is where the main differences are in a VHP cycle compared to an ethylene oxide cycle. So as I said, in ethylene oxide, you typically get just one big inject of ethylene oxide to your set point and then hold it there for a number of hours. Whereas with VHP, we'll pull down to our 4 millibar vacuum, then inject VHP into the chamber until we hit our humidity limit, be it 80% or 95%. We'll then hold it there for maybe a 5 or 10 minute dwell, and then pull our vacuum back to 4 millibars and repeat this again so that we go on pulses. The idea of these pulses is that since VHP doesn't penetrate quite as well as ethylene oxide, our first pulse will push the VHP partway into your product, pulse 2 pushes it further again, pulse 3 further again. So the more challenging a product is to sterilize, the more pulses we'll need. Following this then, we go into our post-conditioning, which is basically just get the hydrogen peroxide out of the chamber again. And this is done through the use of air pulses, steam pulses, or just a maintained vacuum for a set period of time, or typically it's a combination of all 3. And this makes sure then that our residues are kept within our acceptable limits, and once we open the chamber, we're not just releasing a cloud of VHP into the room. Here then we have some typical examples of products that we'd see with VHP, both for ourselves and AST and our life sciences colleagues. And this is by far not an exhaustive list of everything being processed with VHP, it's just the most common ones that we'd see. So these would include things like sensitive drugs in pre-filled syringes that take advantage of how VHP is a strict surface sterilant, as well as being able to operate at lower temperatures. We'd also see novel drug delivery devices, implants with electronics, orthopedic implants, as well as 3D printed implants that are only ever going to be done in small volumes. So you'll never need a 16 pallet EO chamber to process them. And then finally, we'd get a lot of subcutaneous sensor patches as well. As I said, this isn't at all an exhaustive list of everything we do, it's just the most common products that we'd see with VHP. These here are some of the main advantages and disadvantages that come with processing with VHP. The advantages being that we have very good material compatibility. As I said, VHP is very compatible with most plastics, glass, and metals. VHP also operates at lower temperatures than ethylene oxide. So a typical EO cycle could be 50 or 60 degrees Celsius, whereas VHP can go down as low as 28, which is very good for any temperature sensitive products that we might see. VHP is also effective against the full spectrum of microbiological contaminants. So it works against viruses, spores, bacteria, fungi, the whole lot. As I said, it's a strict surface sterilant. So again, with the example of the pre-filled syringe, if you have a sensitive inner sector of the product that you don't want touched by the sterilant, VHP will only sterilize the outside of your product and won't get to that sensitive inner area. As hydrogen peroxide breaks down into water vapor and oxygen, we have no issues around fugitive emissions or carcinogenicity, and we always make sure that any residues are kept within our set acceptance limits. When we process with vaporized hydrogen peroxide, there's no problems then with material discoloration or other cosmetic effects such as brittleness, and we have much faster cycle times using VHP than you'd see with ethylene oxide. So an ethylene oxide cycle could be anything from 20 hours plus, whereas, as I said, a typical VHP cycle is between 3 and 6 hours long. As for the disadvantages then, the main one would be that VHP is not compatible with cellulose, so we can't process paper, cardboard or wood. And the main impact of this then is that any products we see have to be presented individually in just their primary packaging. We can't process them in bulk within their cardboard cartons. And I'll talk a little bit more about that again in the next slide. Another disadvantage then is around the limited penetration of VHP down long, narrow lumen surface contact areas of devices. So again, if you have a 2 or 3 foot long lumen that's only a couple of millimeters wide, or a lot of small gaps in surface to surface contacts in your product, VHP will struggle to get through those. And there are some ways of getting around it, like increasing the number of pulses you use, but VHP will always struggle with those kind of things. Finally, then we have a lot more limited vessel scale with VHP compared to ethylene oxide. As I said, you're never going to get a 16 or 32 pallet VHP chamber. The reason for that being that as VHP doesn't penetrate quite as well as EO, and it does naturally decompose into water vapor and oxygen, if your chamber size is too large, VHP won't be able to penetrate to the center of that chamber with enough power to actually get inside your product and sterilize it fully. And then again, if it's too large, there's also the possibility that it could just decompose into water vapor and oxygen before it sterilizes the product in the center. So while VHP is done on much smaller scales than EO, this is counteracted somewhat by our much faster cycle times. So with the 20 hours plus EO cycle compared to a maybe 3 hour VHP cycle, you can get multiple VHP cycles on a smaller volume done in the same amount of time as you get a single larger volume EO cycle. As I said then, since VHP doesn't work with cellulose, we can't process products in bulk within cardboard cartons. And for this reason, we have to present our product just in their primary packaging on shelves of a stainless steel loading cart that you can see here in the top left corner. And as VHP is a strict surface sterilant, this product packaging, be it a pouch or a blister pack, needs to have some sort of a breathable layer, such as Tyvek, that will allow the VHP to pass through that breathable layer, reach the surface of the product to sterilize it, and then be removed at the end while maintaining that sterile barrier. So we present the products laid out flat on the trays of these loading carts. The cart then gets pushed into the sterilization chamber. We run our VHP cycle, and at the end of the cycle, we take the loading cart out and put the products back into their cartons or shipping containers or whatever they're in. So unfortunately, that does mean that there's a lot more manual handling involved with VHP compared to other technologies. That is something that we're looking at in the future to try rectify, but at the moment, it's unfortunately unavoidable. What's the situation then with international standards for processing with VHP? You may be aware that ethylene oxide has its own international standard in ISO 11135, while radiation has its own standard with ISO 11137. Unfortunately, though, there is no VHP specific standard in place as of yet. So currently we're validating using the ISO 14937 standard, which is around the sterilization of healthcare products with pretty much any sterilization technology that doesn't have its own international standard. And while this does give us a good bit of guidance around processing, it doesn't have any technology specific information in it. While this is the case, however, there is currently an ISO Technical Committee 198 working group who are currently drafting a VHP specific document, which will be ISO 22441, and this working group does have several STERIS representatives working on it. In parallel to this then, SEN also has its own Technical Committee 102 working group who are currently drafting a VHP sterilization equipment standard, which will then be similar to EN 1422 for EO chambers. So while we're currently having to use ISO 14937, there are some VHP specific standards in the pipeline. This here is just a very quick timeline of installation of VHP to our Tullamore facility here in Ireland. As at the moment, our Tullamore site is the only STERIS AST site processing with VHP. And we installed our 1 pallet vessel into the Tullamore facility in February of 2018. Of April of that year, the 1 pallet vessel was then commissioned with a full gap installation pack. And then one thing about having to use ISO 14937 for our validations, it caused for us to use the most resistant organism to our technology for our biological indicators, meaning that a VHP BI uses Geobacillus stereotomophilus organisms as opposed to Bacillus atrophaeus that we'd see with ethylene oxide. And for this reason, in June of 2018, we installed a BI test facility specific for testing of VHP BIs to make sure that there's no chance for any cross-contamination between our VHP BIs and those that we use in ethylene oxide. Following then a little over a year of development work and putting together a full quality management system, in February of this year, the Tullamore facility's ISO 13485 BSI certification was updated to include VHP. So we're now fully certified for any customer processing, both routinely and providing validation work. So with this then, as I said, we're validating at the moment using ISO 14937, which is around the sterilization of healthcare products with any technology that doesn't have its own standard. And while this doesn't give us any technology-specific guidelines, it does allow us to validate using the typical half-cycle overkill method that you might know quite well from ethylene oxide validations. And using this half-cycle method contains both microbiological performance qualification testing as well as physical performance qualification testing. The physical performance qualification testing for this validation is pretty much just to ensure that the equipment is capable of providing the required conditions for sterilization. So once the chamber is fully loaded up, it's still able to reach the required temperature, humidity, pressure, and so forth. The microbiological performance qualification testing then is used to identify the number of VHP pulses in the exposure phase that are required to provide full inactivation to our Geobacillus stereotomophilus biological indicators with a starting population of 10 to the 6 bacterial spores. And these BIs are placed in a suitable process challenge device, which means that the BI will be more challenging to sterilize and inactivate than the natural product bioburden on the product itself. And therefore, if we can find the point that gives us full inactivation of this 10 to the 6 spore population in the more challenging process challenge device, then it's almost certain that the natural product bioburden will be inactivated as well. Once we find then the number of VHP pulses that gives us this inactivation of the BIs, if we then double the number of pulses, this will allow us to provide at least the minimum required 10 to the minus 6 sterility assurance level that is called for in ISO 14937. As well as validation work, we can also provide PCD and routine cycle development. And this is available both for STERIS AST customers as well as those that purchase equipment from STERIS Life Sciences for their own in-house sterilization. So if you do decide to go to STERIS Life Sciences and purchase a VHP sterilizer for your own in-house use, while that sterilizer is being manufactured, you can come to ourselves in AST and we can, for example, identify a suitable internal or external process challenge device for routine use. And this is done using comparative resistance testing to ensure that the BI inside that PCD is going to be more resistant to the process than the natural product bioburden. We can also help to identify the routine cycle parameters that will work best for your product. So the most efficient temperature or the required post-conditioning for the end of a cycle, for example. As well as this, we can then determine the number of VHP pulses that are required to give your 10 to the minus 6 sterility assurance level using the same half-cycle method that I went through in the last slide. Finally, then we can also offer trial cycles. So if you are interested in VHP, but you want to make sure that it has no negative impact on your product, we can run a trial cycle with some sample materials or sample products at whatever process parameters you choose. So any set temperature or number of VHP pulses. And then at the end of the cycle, we'll send those samples back to you, and you can do any material compatibility or functionality testing and ensure that everything still works as it should. Finally, then, just around the research and development that's being done with VHP at the moment. STERIS has actually established a cross-divisional R&D team to link our industrial and healthcare business centres, which involves then a lot of collaboration between our STERIS AST, life sciences and healthcare divisions. As all three divisions are using VHP regularly, we're working together to develop VHP in all its processes. So between ourselves, we're studying multiple different aspects of VHP sterilization, as well as its effects on products and materials. And all of this is focused then on continuous improvement of the process. So any developments that come out of any three of these divisions are used to improve all of our process offerings and efficiency, as well as making sure that we can meet any future regulatory requirements. So for example, with the new ISO and SEN standards that are in the pipeline, we can be sure that if any new requirements come out of there, we're ready to meet them already.
Thanks again for joining us today, and this concludes the webinar.